This is the video of worked solutions for the A2 paper for Stats 2. So that's the S2 paper from October 2018, and it's the 73 paper. And again, bear in mind that this has been made before the mark scheme has been released. So I welcome any corrections, and I will put them in the details underneath the video if there's any corrections to be made later on. This is just my best go at it. We start off with a straightforward confidence interval, and 97.5% would mean that we have 1.25% on either end, and that gives us this area that we want to find up to this point here for our z value. So that area there would be 0.9875. So all of this bit here. So that z value that gives us 0.9875 is 2.24. Then we use the formula for doing the confidence interval. So that'll be x bar plus or minus that z value times sigma over root n. Which comes to 174.86 centimeters and 177.14 centimeters. I'd be tempted to leave it like that because of the kind of question being asked. However, you could possibly get penalized for not doing it to 3 significant figures, so we'll just finish it off with that as well. So that's our answer to 3 significant figures. Part 2, the necessary condition for this calculation is that we, of course, are working off a normal distribution when we haven't been told that it is one. So that's our condition for this to work. Specifically, that the heights of the males are normally distributed. Question 2 has a hypothesis test on a binomial distribution, and we need to start off by setting up the null and alternative hypothesis. So the null is that the original probability was a third, and the alternative hypothesis is she's testing if that probability has decreased, so that probability is less than a third. The conclusion in part 2, we have that the probability of that test statistic of 36 that she measured, the probability of that is 0.0084. Now that is less than 1%. So it's less than the significance level. That means we can reject H0, the null hypothesis, and we'll put that into context to be able to make the conclusion, which is to say that there is evidence to suggest that the probability of a healthy lunch has decreased. Part 3 is, according to this model, what's the largest number of children who might bring a packed lunch to school? This was a bit of a weird question in my opinion, and what I didn't spot straight away is that it asked about the largest number of children who might bring a packed lunch. We're not talking about just the healthy ones anymore, just any kind of packed lunch brought to school, which means that's the total number of trials being tested out. So that has to be 150. Now we've been given some information in question 3 that we need to work through to unpack what we need from it. So first of all, x bar is normally distributed with a mean of mu and sigma squared over n. That's our regular distribution for x bar using the central limit theorem. So now if we put in the numbers that we're told in the question, x bar follows a normal distribution with mean of 12 and 2.5 squared over n, and n is what we're going to work out. We're also told that the probability that x bar is less than 12.2 will become equal to 0.975. So I'm just going to put that into terms of z first. So this would be 12.2 minus 12 over the square root of 2.5 squared over n. That's to equal 0.975 as specified in the question. Well, phi of 1.96 is what gives us 0.975. Therefore, 12.2 minus 12 over the square root of 2.5 squared over n has got to be less than 1.96. So if you rearrange that, you get n is less than 600.25. N is equal to 600. Now, if you're not sure about the inequality and which way around it goes, you can work that all through as an equals, and then at the end just test out what works, whether 600 or 601 is what you were looking for, and you'll know which way around to put that inequality. Okay, so A and B are randomly and independently distributed in the air, so they are distributed within a set space. So this will be a Poisson distribution for each of those. So in 1 centimeter cubed, that's what they will look like. And if we let a new variable of t, which would be if we do a plus b, then t will be also distributed following a Poisson distribution, just by simply adding those two together, which gets to 0.61 in 1 centimeter cubed, which means that if we now do t subscript 10, that will follow Poisson distribution at 6.1 in 10 centimeters cubed. Now we're working out what's the probability that t in 10 centimeters cubed is greater than or equal to 4. That'll be 1 minus the probability that it is less than or equal to 3. So that's 1 minus the probability that t can be equal to 0, 1, 2, or 3. Which works through to 0.857 to 3 significant figures. Part 2, we're going even bigger, so just multiply that up for the space of 100 centimeters cubed, and we want to work out the probability that that new total is less than 60, but that's going to be too tricky to do as a Poisson distribution, so we need to approximate it with a normal. So then the probability that this new total will be less than 60 becomes the probability that z is less than 59.5, because we're not going to use the 60, we need to apply that continuity correction, minus 61. Remember that continuity correction is because we've turned a discrete distribution into a continuous one. So we had it originally was going to be at this 60, and anything less than that 60 not including it. So take half off, you get 59.5. So minus the 61 and then over the square root of 61. So this comes to phi of minus 0.1921, which is 1 minus 0.5761, gives us a final answer of 0.424 to 3 significant figures. We're continuing the theme of linear combinations here on question 5. So this one is now with normal distributions. And we're looking at doing one of each type of house. So that's T1 and T2. Add them together for the total time it would take to do them. So that will now follow a normal distribution where we add together the means. So that's 2.2 plus 2.8. And we also add together the variances. So we have T1 plus T2 now follows a normal distribution of 5 and 0.41. We want within that distribution, what's the probability that that total time will come to less than 6? Which is 0.9408. Now just a reminder from the previous slide, Q's times were T2 and P's times were T1. Now this one is asking us, what's the probability that the time for a Q house, T2, will be more than 1.2 lots of the time for a P house, which is T1. Now if we rearrange that, we can have it to be 1.2 T1 minus T2 is going to be less than 0. We want to find the probability of that happening. So if we do this as a new distribution, then 1.2 T1 minus T2 will follow a normal distribution I'm actually going to need a bit more room, so I'm just moving it over. And we're going to have, now to get the means of this, we will do 1.2 lots of the mean for T1, take away the mean for T2, but the variances, it's going to be 1.2 squared when you multiply variance by a constant. That constant gets squared, and we add together the variances for the two different times for the houses. Even though we're doing a subtract teacher, the variances still get added. So that's our distribution, and what that becomes, I'm just going to write down, let's see, so this becomes that 1.2 T1 minus T2 follows a normal distribution with minus 0.16 and 0.4804. So continuing now to work out that probability of that becoming less than 0, this will be the probability that Z is less than 0, take away the mean, which is minus 0.16, over the square root of the variance, which becomes phi of 0.2308, which is a probability of 0.5914. Now question 6 is quite nice because they show that question, so you'll know that you've got it or not because you'll have got to the answer. So the integral between 2 and 6, so over the whole range of this function, is going to equal 1. So if we pop that in, integrating 1 over x gives us log x between 2 and 6. So that becomes k of log 6 minus log 2. Using our log rules, that gets us k log 3. So we know that k log 3 has to equal 1, therefore k is 1 over log 3. Now to do e of x, we go between 2 and 6, integrating again, but of x, f of x dx. So that's now, we know what k is, so we'll take out the k, and it'll be x times 1 over x dx, which of course is just 1. So when you integrate that, you will get x between 6 and 2. And if you work that out, you get 3.64. Now I was so pleased when I saw this question because I put one identical to this, of course slightly different numbers, but on our practice paper for this year. So this was in the mocks. Right, so the median, any value from 0 to the median of our function, the probability of that is going to be equal to 0.5. Okay, so if we work out from 0 to, not from 0, our function starts at 2, hold on, let's just fix that up. So from 2 to e of x, which we just worked out as being 3.64 of our function, and carry on with that, and then we'll just have to take off the half. So that integral there, we've got 2 to 3.64 of 1 over log 3 x to the minus 1 dx. And then evaluate with the, and that comes to 0.5451. So then the integral between m and e of x to give our probability will be to do that 0.5451, because that's everything up to e of x, take away everything up to the median, and that gives us 0.0451. Now finally, question 7, we have a null hypothesis that the mean is equal to 51, an alternative hypothesis that the mean is not as stated, and in fact it's less. So it's a one-tailed test, so mu is less than 51. x bar is originally stated to follow a normal distribution with 51 and sigma squared over 150. We haven't been told sigma squared, so we'll need to work out an unbiased estimate for that variance. And you have that formula on your formula sheet. And that comes to 46.96, so that's what we are going to estimate our variance to be. So we reject at the 2.5% significance level. That means we'll reject if Z is less than minus 1.96. So if we put that in terms of x, be x minus the 51 over the square root of 46.96 over n, which is 150, that's got to come out to be less than minus 1.96 for the rejection region. So that means if x is less than 49.9, we will reject the null hypothesis. So the mean from the sample, and actually I should have written x bar on each of those. So the mean from our sample that we use to test this against, we'll take from doing sum of x over n. That gives us 49.87 as the mean for this sample. So our conclusion is that our sample mean is in the rejection region, therefore we will reject the null hypothesis. And there is evidence to suggest the mean is less than the claimed 51 kilos. Then we're given the situation of what the actual population standard deviation and mean is, and we're asked to work out the probability of type 2 error, which is that we've accepted the null hypothesis when the mean has actually changed. Now on the previous slide we worked out that critical region as being 49.9, which means we will accept H0 if x bar comes out to be more than 49.9, so we want the probability of that happening on this new setup of the distribution. So there's our new distribution, and we're working out the probability that x bar is greater than 49.9. And that comes out to 0.054 at the end. And I've just realised that I've worked it out not to 3 significant figures, so just add whatever third decimal needs to be there.